Where were we?
Gibbs.
Yeah, Gibbs. Right. So.
This is where we jump from.
Yeah. So we're at this idea now of free energy. And the one that we really care about in chemistry, there's actually two free energy equations that you often see in chemistry. And the one that you see the most, of course, is Gibbs free energy, delta H minus T delta S. And the idea is that if delta G is less than 0, the process is spontaneous. Right? The system generates enough energy, enough heat to pay the entropic costs. And so it goes to completion. Whether that means right, either the surrounding environment has to increase its entropy or the system does. So if the system is more ordering as you go to completion, then you have to release enough heat to make the entropy of the outside environment be greater than 0, which means delta H needs to be negative, appreciably negative to make this delta G less than 0. Right? Delta S has to be greater than 0 somewhere. And of course, if delta G is greater than 0, that means there's some left that the process doesn't have enough heat in the bank account to pay the tax. Right? So this is a non-spontaneous process at this temperature. And then, of course, there's the condition delta G equals 0 as well. And we call this equilibrium, which means that the system can proceed forward and backwards at the same probability. Right? It's equally likely to go to completion as it is to go backwards. Right? We'll look at this region delta G equals 0 a lot when we get the equilibrium, and phase transitions next week, starting next week. All right? So we'll look more at this condition later. But a really nice thing is that things that occur at equilibrium, that you can write delta S, for instance, as delta H over T. Right, so for instance, if you have a phase transition, so for instance at a phase transition, so for instance for water, liquid to gas occurs at T equals 373.15 Kelvin. At this temperature, delta G for this reaction is 0. Right? That's at the boiling point. Right? And we'll see that when we get to phase transitions. This is a classic example, is the phase transition occurs when delta G changes sign for the conversion. Right? So for temperatures lower than 373, this transition has a delta G greater than 0. So for, let me write T less than 373, delta G is greater than 0. T greater than 373, delta G is less than 0. Right? Changes signs. Right, and that's we'll talk more about the thermodynamics of this effect later. But the nice thing is that if you can measure the temperature and how much heat this releases or absorbs, right? If you can measure delta H for a phase transition, which is, if you're in PChem lab right now, you can just do calorimetry to measure that delta H. You can measure delta S. And the reason why is because delta G is equal to 0, which is equal to H minus T delta S, which means at the phase transition, delta S is equal to delta H over T. Okay, so you can measure that. That's a really nice place to measure entropy for a reaction. If you can find the place, especially for a spontaneous reaction like a phase transition, it's a really good example. You can always relate enthalpy and entropy very easily because at that point delta G is 0. Okay. So we'll look at this a little bit in class today. What I want to focus on though is that we're going to use delta G in a lot of different contexts as we go forward, and I don't really want to spend a lot of time on that right now because the important parts about delta G is it just kind of tells us the order at which, the direction at which a process goes, right? in some ways, you could say delta G is less than 0. The process wants to move forward. Delta G is greater than 0. That means it wants to move backwards. Delta G is 0, then it's equally likely. And in some ways, this typifies everything that you need to know about delta G. But eventually, we're going to want to be able to calculate this for more complex systems other than just one component converting into another one. So we'll come back to that, looking at how you measure delta G for multiple component mixtures and things like that. Maybe you want to look at, for instance, in CHEM lab, you're doing right now in the rotation is looking at the solid liquid phase diagram for a mixture of naphthalene and biphenyl. And delta G is a little more complicated there because you've got to deal with the relative contributions of the naphthalene and the biphenyl. And as you add more of one to the other, then the thermodynamics changes of that mixture. So we'll look at that very carefully when we get to that point. But what I want to focus on today is this idea of measuring delta S, right? Because what we want to do in chemistry, ultimately thermodynamically, is measure delta G. Right? This will end up telling us a lot about what's happening in a reaction or any sort of chemical process. And maybe we want to come up with a way to generate a new molecule, right? Some new reaction to form some novel molecule. And we need to predict whether that reaction is going to go thermodynamically or not at a given temperature. We've talked a little bit about calculating delta H, right? We can use enthalpies of formation. The question is, how do we calculate delta S? Right? How do we come up with an entropy value of formation, if you will? The equivalent of an enthalpy of formation, but for entropy instead. So that's what I want to talk about today. And we'll come back, we'll spend a little bit more time on entropy and how we measure it. And thankfully, there's a thermodynamic law that helps us immensely with this. So in fact, we're here at the third law, the third and final law, which allows us to define exactly how we define entropy in terms of a number. Right? The idea was, for enthalpy, remember, was we had to find a zero level, right? What enthalpy equals 0 at, right? What do we compare to as an absolute scale? And turns out the third law tells us exactly what the absolute scale of entropy is. The third law, there's a couple different ways to write this. One is from a famous chemist named Nernst. It says that for perfectly ordered substances, like a crystal, delta S goes to 0 as T goes to 0. Okay, so if we can take what we call perfectly ordered substance, who knows what that is, but we'll come back to it, and we can drop it down to 0 Kelvin, then we know for a fact that entropy is 0, right? So that's nice because with enthalpy, we didn't really have a definition of what what H equals 0 means, right? We had to define a scale to reference against, which is why we use enthalpies of formation. But entropies are really nice because entropy is going to go to 0 as T goes to 0 for most species. Okay, so we can always, for instance, we can extrapolate, we can measure entropy as a function of temperature, which I'll explain how we do that when we get to it. And we can extrapolate down to T equals 0 and we can get a sense of what the entropy is. Another way to write this is more of a definition of what we mean by a perfectly ordered system. Did I spell corollary right? No, I did not. Corollary. Which is that the entropy of all perfect crystals at T equals 0 is S equals 0. Okay? So, for instance, we're going to want to reference for any species, right? Maybe we have bromine or carbon or something like that. If we want to think about what we reference its entropy relative to, we're going to take the crystalline form of that and freeze it all the way down to 0, and that'll be our baseline, right? The idea is that S is equal to 0 there. And the way that this works, let me get a picture of a nice crystal for you, because God forbid I can actually draw this. Let me draw a diamond crystal structure. Crystals, in fact, have a very rigid structure, right? So diamond, for instance, is what's called a face-centered cubic structure. crystal. And the way that it looks like is just literally a cube. Right, and where each vertex of the cube is a carbon atom. Did I get all of them? Yeah. All of them are carbon atom, and then there's some amount of carbons inside as well. But every unit, I don't know what they look like exactly, but the idea is that you have a symmetric structure. It's a really poor picture, but every unit, basically a crystal of diamond, a single crystal diamond looks like this. It's got some fixed number of carbons inside of it, and a larger diamond. This is what's called a unit cell. This is the smallest indivisible part of a crystal of diamond. And a larger diamond is just adding more of these on top of it, right? So there's only, the idea is that, right, we can just keep, all you do is you just keep adding these together in a structure and pack them together as the crystal gets bigger and bigger. So the size of the structure, basically you have a unit cell that's repeated over and over again. And so the structure of a crystal is fixed, right? There's really no way for, theoretically, if there's no energy, right? If the T equals 0 is no thermal energy, there's no way to rearrange this system at all. There's only one arrangement of a single unit cell of diamond, and it looks like this, for instance, roughly like this, right? And so since there's only one arrangement, then the entropy is 0 at T equals 0, right? There's no thermal energy to make the bonds move. Right, so T equals 0, no thermal energy available for vibrations, right, for the system to vibrate and to wiggle like this. And so all the system can do is just sit in this cube, and that's the only arrangement it can have. So when you think about entropy being KB ln W, or W's number of arrangements, W is 1 for a crystal. So therefore, entropy is 0. Right? So that's the idea that Nernst and Boltzmann had, was that a crystal in some ways is the most rigid and the most indivisible way to represent an atom or some material, because the way that crystals work is that you always have this fixed unit cell, and all that happens when you make a bigger crystal is that you just, what they call tessellate them. They just stack them on top of each other in a pattern. Right? In some ways, all a big crystal is just a quilt of smaller unit cells. And so there's only one arrangement for a crystal, and so the entropy is 0 by definition. It turns out that this isn't always true, unfortunately. Not all crystals actually have 0 entropy at T equals 0. So not all real crystals have S equals 0 at T equals 0. Of course, another definition of the third law, I don't remember who this is from, but the idea is that it takes infinite steps to cool a system to 0 Kelvin. So in fact, getting something to absolute 0 is impossible. So if you were to take the thermodynamic steps like compressions and expansions over and over again, you have to do infinite of them to remove all of the energy from the system. So there's no real way to actually measure anything at 0 Kelvin. You have to extrapolate. Right? You can measure it at 4 Kelvin, 5 Kelvin, 10 Kelvin, and just connect the curve to 0 Kelvin, and you can predict what it is at 0 Kelvin. But another way to write this is it's practically impossible to reach absolute 0. So we don't actually can ever measure anything at 0 Kelvin, but we can predict what it looks like at 0 Kelvin by looking at data at other temperatures. And for instance, not all real crystals have S equals 0. For instance, the entropy of graphite solid graphite at 0 Kelvin is 5.7 joules per mole per Kelvin. Right? It's a very small number. That's not a lot of energy, but it's still there. Diamond, it turns out, actually does have some symmetries that cause you to have more arrangements than what you would predict, but a very few. 2.4 joules per mole per Kelvin. And interestingly, ice, water ice, as we'll learn when we get to phases, there are many different types of water ice, but the most common ice, the one that you find in your freezer, ice 1, has some residual entropy of 3.4 joules per mole per Kelvin as well. Okay, we'll talk a little bit about why this is. But the idea is, the nice thing is that even though we know that the entropy at 0 Kelvin might not be 0 for a real system, we can measure it pretty easily by extrapolating. I'll talk a little bit about how you do that measurement. Okay, but so a lot of things don't have, so typically we reference our entropies relative to these numbers for these species, which are of course not 0, there's some fixed number, but they're well-known numbers. There's another standard that we use. Question? Sorry? Or just talking, okay.
Sorry.
No, that's okay.
What does it say?
next to H2O?
Oh, crystal, H2O,
Oh.
ice 1.
Yes.
The ice 1 crystal. Yes, it's crystal, CR. I apologize, yeah. Yeah, CR is the symbol for crystal. In the same way that fancy L is liquid, S is solid, and so on. That's what crystal, you're welcome. Yeah, I'm sorry, that's not a common notation. So we have to unfortunately, we kind of have to define a standard for entropy. We have a kind of a good sense of how we do that with crystals, but that's not always a great way to do things. Because, like for instance, if you're working with liquids, you don't want to really deal with crystals. So there are some other ways that we define reference points for entropy. So in aqueous solutions, there is a unique definition for 0 entropy. IUPAC, the International Union of Professional and Applied Chemists, defines the molar entropy for a solvated proton, H+, as 0 joules per mole Kelvin. So when we're dealing with aqueous solutions, remember that water has some equilibrium between OH minus and H plus like this. Right? And if you were to measure the entropy change of this reaction, the standard entropy at 298 Kelvin for H plus is 0. Okay, so that's a really common definition for the 0 point. You reference everything relative to a proton, an acidic proton, or H plus. Remember, the reason why I call this a proton, in case you forget, is because a hydrogen atom in its regular state is 1 electron, 1 proton. So H plus is 0 electrons and 1 proton, right? So often I'll call H plus a proton because that's all it is. It's just a proton, right? So the definition of a solvated proton is 0 at 280 Kelvin. I want a 0.0 joules per mole per Kelvin. It's a really nice kind of standard to use because while we reference everything relative to water, this is a really well understood reaction, right? This is what we define pH by. We understand this equilibrium very well, so it seems natural to define entropy as 0 for H plus because it's easy to measure the thermodynamics of acids. It's kind of the classic thing that we do. Right? By measuring equilibriums and pHs and stuff, you can know everything you need to know about the thermodynamics of water. However, when I look at this, I get triggered. Because this is a terrible way to define things. I hate that they define it this way. And let me tell you why. It's because when you go do spectroscopy, on the process of solvating a proton, so you think about the entropy change of water when you add a proton to it, that the entropy of solvation, right? So this is the solvation change, the entropy of entropy change when you add a proton to water, H plus AQ. This is actually ordering. They measure a negative energy change. So the interesting thing is that when you take a proton, a free proton, and you put it in the water, the system orders itself by 21 joules per mole per Kelvin, which is a pretty big number. I mean, comparatively to a crystal, right? This somehow provides 4 times more energy per unit Kelvin in the opposite direction as the entropy of a crystal, of a diamond crystal, right? It's almost 10 times even, right? And so it seems odd that we would reference everything versus as this is 0, when in fact it's actually a negative number. And the reason why is actually really beautiful why it's negative. The reason why is because there's multiple ways that a proton can exist inside of water, in liquid water. And this ordering causes, there's ways that water will arrange itself around a proton, and that's an ordering effect. So for instance, so let me write this. The presence, there's a lot of beautiful papers on this, and it's been studied for a long time, but the presence of a solvated proton induces ordering structural changes to liquid water. Right, what we often say is that water creates a solvation shell around the bare proton. So water, when regular old water interacts with a proton, it rearranges to kind of encapsulate the proton. And in fact, it does it in 2 different ways. There's a dynamic equilibrium of 2 different dominant structures of water around a proton in liquid water. And you can study these with spectroscopy. There's a professor at Yale named Mark Johnson who spent his entire career building instrumentation, mass spec instrumentation, infrared spectroscopy, a combination of the 2, to study the influence of protons and charged species inside of liquid solutions. And so he's the kind of guy who actually measures these things spectroscopically and shows how the structure of liquids change when you introduce protons into them, right, in an acidic solution, if you will. And it's a really beautiful piece of work. But what you find is that there are 2 dominant structural motifs in solvated protons, and they kind of look like this. Let me draw a different color. So what you have in the middle of the first one is an H3O plus. Let me draw this a little lower so I have more room. So here you have this H3O plus molecule in the middle. This is your lone proton. I'll color it in blue. This is your proton. And it hydrogen bonds to another water. See if I can draw this, like so. And this one here donates to another water, like this. And then you have another proton donor to hydrogen bonding. So it looks like this. Okay, so this is like, so a solvated proton, the solvation shell has 4 water equivalents of water, right? 1, 2, 3, 4. and you have a central H3O motif in the middle. Right? And this is what's called the eigenstructure. After a man named Eigen, I think. That's one of the common structural motifs you see in liquid water with a proton, acidic water. And there's another one that is much simpler. Which is just a single H3O plus, H3O plus, interacting with a single water molecule like this in plane. Right? This is called the Zundel structure. Right, so the water exhibit, so when you look at a proton spectroscopically, you see two signals for this OH plus stretch. Right, we're going to monitor this stretch of IR spectroscopy. Right, the OH stretch. Right, we can monitor this one too with IR. And what we see are two distinct signals. One for the eigenstructure, one for the Zundel structure. They have different characteristics, different strengths, and so they show different bands in the IR spectrum. Right? So it's very clear that two of these exist, but the really beautiful thing about them is that they're interconverting all the time. There's a dynamic equilibrium between the two. And in fact, what happens is that, so the cool thing is that you see this typical Bronsted-Lowry H3O plus in both structures. Right? When we talk about this is Lewis acid and Lewis base in some ways, and this is Bronsted-Lowry. They're equivalent. They tell you the same things. So we see that kind of dominant H3O plus structure in both of them. But this H3O plus is very transient. It doesn't exist for very long. And the system interconverts. So let me say this again. Liquid water, acidic water interconverts between Eigen and Zundel structures on a time scale of about 10 to the minus 14 seconds. Really fast. It's about 10 to the minus 15, 10 to the minus 14, depends on the solution. All right, so, bless you. So what's happening is when you put this proton into water, it arranges the water around it into these fixed structures that are ordered, right? These waters are now fixed in some way to this proton. They're associated with it. You've ordered the local water region to surround itself with the H, and it interconverts rapidly between these two energetically favorable structures, and this is naturally an ordering process. Delta S is less than 0 for this, right? Because you've ordered the water around the proton. And so this is a very fast interconversion. These are both fairly stable. You see both in your solution, and the fact that the system equilibrates between them as a delta S is less than 0 process. It's an ordering process, which is why you measure a negative solvation entropy for a proton. Because in fact what's going on is that the system's actually arranging itself to support that proton. Okay, so I really hate when it's written like this. But the reason why this is like this is when we get to electrochemistry, it will become very clear why we do this. Electrochemistry will talk about the oxidation potential or the reduction potential of a species, the ability or the energetic impetus for it to accept or donate an electron. And we'll find that H plus is kind of the standard that we use for that. It has a voltage of 0. So it has no impetus one way or the other to donate or accept the proton. It's the standard that we set. So that's why we set the energetic standard for entropy to be 0 for H plus, because it works well for electrochemistry. But in terms of a physical chemistry perspective, saying that H plus is, this is again aqueous, H plus's entropy is 0 in aqueous solution really misses the beauty in the physical reality of liquid water, which is that liquid water is not just this dumb random liquid, just everything flowing around randomly. It has distinct structures that exist in it that interconvert rapidly. They're moving around fast, but these structures exist for some amount of time scale, and the system samples between both of them. These are real things. Right? And that naturally has an ordering effect, and so delta S should be less than 0. Okay? So this is why organic chemists and I don't get along that well, because we see two very different perspectives here. So the idea is here, this is kind of a physical interpretation. And this idea of setting it equal to 0 is for convenience. For convenience. It's just for convenience. It just makes it easy. And to be fair, this wasn't fully understood until the last 20 years or so. This really requires very sensitive, and actually, Mark Johnson's work at Yale is beautiful. He's an incredible machine, incredible instrumentation, does really, really sensitive work with mass spec and infrared spectroscopy. And so this is really kind of a big achievement in physical chemistry, is understanding the structure of liquid water or proton. Okay, questions? Okay, so I want to talk, let me pull up one more sheet. Hopefully I have it. Yeah, so I want to talk, so that's kind of the sense of where we set S equals 0 to, right? This is our reference, that 0 Kelvin means entropy is 0 for a perfect crystal, and we can reference everything to that, right? That's it. And so enthalpy, again, is always defined kind of arbitrarily, what enthalpy equals 0 is, but for entropy, we have it's naturally connected to temperature, right? As temperature decreases, entropy decreases. And in general, S goes to 0 as T goes to 0, as we said, but as T goes to infinity, S increases monotonically. It never goes down. Right, so as we'll see, if you plot entropy, temperature versus entropy for a species, it won't look like that, but it'll always kind of go up and eventually it'll start to level off. It'll always increase. Okay, so that's really nice, because we know that if it has this monotonic behavior, that it's always moving in the same direction. The derivative always has the same sign, right? Derivative of ds dt is always greater than 0. We can always extrapolate down to t equals 0 and get a good sense of what the entropy is at low temperature, and vice versa, we can go up. So let's talk a little bit about understanding how we get this. And I have a couple nice examples on how we measure entropies at different temperatures. Okay. So before we jump into that, let's go ahead and do the entropy first, I guess. I'll make this different. So let's think about how does entropy change with temperature. Okay, so let's do some analysis. All right, so we'll start with the first law, which says that the change in energy, total energy, is equal to, again, the change in work plus the change in heat. Sorry, I had this flipped, but change in heat plus change in work. And by the second law, we can rewrite change in heat as TdS, and work, of course, is minus PdV. So this is a really good equation to remember, that the change in energy is always TdS minus PdV. It's a really nice equation to have. This enforces positive entropy for a system and negative work. It's the opposite sign convention that we used earlier in class, but it's equivalent. And so let's think about let's think about let's set dP equals 0, isobaric conditions. right? So we can use enthalpy and Gibbs energy. Right, and so the definition of enthalpy is, remember, let me start over. Enthalpy again is U plus PV, which means dH is equal to du plus PdV plus VdP. This is the product rule. Right, we're taking the derivative of PV, so you take P times the change in V plus V times the change in P. There's a product rule going on there. And we can plug in this for du. So du is TdS minus PdV plus PdV plus VdP. Again, these cancel out. So you're left with TdS plus VdP. But dP is 0, so this goes away. TdS. Right, so dH, so the change in enthalpy is equal to the change in entropy times temperature. Right? Oh, this is just the second law, right? If you divide both sides by temperature, you have the change in entropy is the change in heat divided by temperature, which is just the second law. And so not really saying anything fancy here. Now what I want to do is take the derivative with respect, right? We want to see how this changes with respect to t. So we want to calculate ds dt, the change in entropy with respect to temperature at constant pressure. So we'll take the derivative on both sides with respect to temperature. So we have dH dt at constant P is equal to T times the change in entropy with respect to temperature, constant P. Right, that's what we want. Right, so that means that ds, the change in entropy with respect to temperature at constant pressure, is 1 over T times the change in enthalpy with respect to temperature, constant pressure. But we know this term already. This is the heat capacity at constant pressure, right? The change in energy with respect to temperature, right? How much energy does it take to raise, or how much enthalpy or heat does it take to change the temperature by 1 degree at constant pressure? It's just the heat capacity. So therefore, ds dt, the change in entropy with respect to temperature at constant pressure, is just the heat capacity of the material divided by temperature. Right? So that means then that this curvature is right? So as temperature increases, the slope of this is the slope of entropy with respect to temperature. So as temperature, let's assume Cp is constant, it's just a number. So as T increases, the slope gets closer and closer to 0, right? As T gets bigger, this gets smaller and smaller. So that means that at infinite temperature, there's an asymptote, right, that it approaches, which is S max, which is the entropy at T equals infinity. Right? So there's some maximum entropy that the system will approach at infinite temperature. Right? So the whole thing kind of levels off. This is just kind of a good approximation for it. Of course, as we've learned, heat capacities might be temperature dependent. So for some species, you might have to change that, and so the slope might get weird, because this might be a function of T. But if you assume Cp is a constant value for a species, then you already know what the slope looks like. So assuming Cp is constant, we can integrate both sides of this. We can multiply both sides by dt, and we have ds is equal to Cp over T dt. And so we can integrate both sides of this. So that's going to be the integral from initial to final. We'll call it from Si to S final of ds is equal to the temperature integral from Ti to Tf of Cp dt over T. So S final minus S initial, which is delta S, is equal to Cp, right? It's just a number, we can bring it out. Ti to Tf of dt over t. And this is just the logarithm of t. So super easy. I'll rewrite this out. We have a really, really nice equation now. Is that if we know the heat capacity of a substance, we can calculate the entropy of it at any temperature. So for constant heat capacity, entropy at T equals T final minus the entropy at T equals T initial is equal to the heat capacity times the logarithm of the ratio of the temperatures. Okay. And if heat capacity is a function of temperature, then S of T equals T final minus S of T equal T initial is equal to the integral of Cp, a function of T, divided by T dt. Now look, the cool thing is that the enthalpy, this is Kirchhoff's law that we talked about earlier, is exactly the same. Well, not exactly the same, but has the same formalism. This is just Cp of T dt. Right, so the only difference between measuring the change in enthalpy between two temperatures and the entropy is just taking 1 over T, right? And that's just the second law, right? The second law says at constant pressure, the change in entropy is equal to the change in heat divided by temperature, which is the change in enthalpy divided by temperature, right? So there's really nothing special going on here. I've done a bunch of math, but in fact, all we're doing is just taking 1 over T, and we can convert from enthalpy to entropy at constant pressure. Okay, and so it's typically, we talked about with this is, remember, this is called Kirchhoff's law. Kirchhoff's law, the entropy, Cp of T, is usually expressed as a polynomial in T. So it's, T squared plus T cubed plus T squared plus T plus a constant factor. It's just a polynomial. So the integrals are pretty straightforward, and you can come up with these heat capacities experimentally. And you can measure the heat capacity of a substance as you increase the temperature, fit a curve to it, and then you can calculate the enthalpy of that material and the entropy by just taking these integrals. It's super easy. It's really beautiful how this all kind of works out, right? The entropy is just the heat divided by temperature, right? Exactly what the second law tells us. So as a motivating example for this, I want to talk about a really interesting problem. So again, just as a reminder, standard entropies, right, the ones that you find in a book for substances, are referenced at T equals 298 Kelvin and P equals 1 bar. Okay, so when you go you can go look up in the back of Atkins, for instance, or on our NIST webbook for these entropies for substances, just like you look up enthalpies, and they'll be expressed relative to 298 Kelvin and 1 bar, right? Standard temperature and pressure. Okay. So typically, Ti is typically 298 Kelvin. Typically 298. You can look them up through NIST, just like there are entropies or enthalpies for all different types of species. There are standard entropies for substances as well. And they're measured the exact same way. Just you take 1 over T and integrate. Bless you. Okay, now I want to show you a cool example. Okay, great. This really drives home the power of state functions, I think. And the question is that we want to measure the standard entropy of a substance that doesn't exist at standard temperature and pressure. Okay? So for instance, what if we take bromine liquid and we want to convert it to bromine gas at T equals 298 Kelvin, and we want to ask the question, what is the standard entropy of bromine gas? All right, what is the temperature of bromine, what is the entropy of bromine gas at 298 Kelvin? The problem is bromine liquid does not boil until T equals 332 Kelvin. Okay, so we want to, right, well, maybe we want to tabulate these entropies where we've been assigned to measure standard entropies for different materials. And of course that means we got to define them at 298 Kelvin, but how do we do that for a species that doesn't exist at 298 Kelvin? Bromine has a vapor at 298 Kelvin, but that's a different issue altogether. But how do we just look at the gas when there is no gas at this temperature? And so there's a really clever way to do this. What we can do is use the fact that entropy is a state function. So it doesn't matter which path we take from initial to final. Let's come up with an easier path. So why don't we do this? Why don't we heat liquid, we'll call this step 1, heat the liquid to T equals 332, to make bromine liquid, and then watch it vaporize at the boiling point. Okay? And then bring it back down by cooling it. T equals 298 Kelvin. We'll call this step 2 and this step 3, right? So the entropy change here is just going to be the entropy change of the 3 steps. Right, we start here, we add the entropy change here, add it here, and we get to the final one. Okay, so let's do that calculation real quick. This is how we get around these problems. And next Monday, I'll give you some more examples. We'll talk about some more thermodynamic kind of measurements and things, different applications of this kind of technique. And to measure really, really fundamental energies, like how much energy does it take to break a bond? Typically, chemists don't just go into the lab and set it up to break a bond. Rather, they define a loop of extra steps, a longer path of easier things to measure that when you add them all together, the net is just the path that you want. Okay, so I'll show you some examples on Monday of this as well. So the idea is that because it's a state function, you can take any path you want. So let's make it, instead of making it do something hard, one step that's hard, let's do 3 steps that are easy. And we know that they're all going to add up to the right thing. So we're going to need some material, we're going to need some information for this, some numbers. We're going to need some heat capacities. Right? And we're also going to need to know what the entropy at the starting point is. What's the entropy of bromine liquid? Well, that's easy to measure because there's lots of bromine liquid at 298. You can measure it pretty straightforward. So the entropy, the standard entropy of bromine liquid, just look it up in a book. 152.2 joules per mole per Kelvin. And we need some heat capacities, right? Because our calculations for changing entropy and enthalpy require heat capacities. So the heat capacity of liquid bromine, again, you can measure this easily with calorimetry, is 75.69 joules per mole per Kelvin. And we need the heat capacity for gas. Which is 36.02 joules per Kelvin per mole. Now convince yourself, it should be clear why the heat capacity of the gas is lower than the liquid. Gas doesn't have nearly as many degrees of freedom. There's not as much motion that a liquid bromine gas or bromine gas can do. There's not enough states that it can exist in, so the heat capacity is lower than it is for liquid. Liquid can absorb more heat before it increases the thermal temperature, okay, which is why it's about twice. Okay, and this is enough information for us to calculate the entropy of bromine gas at 290. So let's go ahead and do each step. So we'll start with step 1, which is heating. And we know how to do that. Entropy change along path 1 is going to be the entropy of the liquid. So I'll write entropy of the liquid at 332 Kelvin minus the standard entropy of liquid 298. All right. This difference again is going to be the heat capacity of the liquid times the logarithm of the ratio of the temperatures. That's what we derived. We're assuming the heat capacity is constant here, which is it turns out to be the approximation for bromine. The change in the heat capacity going from 298 to 330 is very negligible. So we just assume they're a fixed number. So it's the CP, the heat capacity of liquid, times the logarithm of the temperatures, and just plug in 75.69 times the log of 332 divided by 298. I won't even do that math out, but it's 8.140 joules per Kelvin. Now let's do S2, which is the phase transition. Okay, and in the phase transition, before I write this is step 2. We know that delta G is equal to 0, right? That's what I kind of mentioned at the beginning. That a phase transition that gives free energy is 0, which means that delta S is equal to delta H minus T divided by the temperature. Did I miss a number here? Yeah, I forgot to write a number down. So you can measure, this is the vaporization enthalpy at the temperature of vaporization, which is 332. You can measure this by looking how much heat is released or absorbed by the system. So this is easy to measure. I forgot to write the number down. Measure with calorimetry. So when the enthalpy change of vaporization, you're going from liquid to gas, which means that you need to bring in energy to break the liquid apart. So enthalpy is positive. This is greater than 0. It's an endothermic transition. We'll talk more about that when we get to phases. But delta H for liquid to gas is always greater than 0. Right? The system has to bring in energy to break the liquid in. So delta S, of course, is greater than 0, which means that delta S vap is greater than 0. Right, and that should make sense that delta S for vaporizing a liquid is greater than 0 because you're going from an ordered liquid to a disordered gas, so delta S is going to be greater than 0. And so here, I'll just write it down. I have the result. Delta S for vaporization is 88.98 joules per Kelvin per mole. We could calculate H vapors from this by multiplying by T vap, but we don't need to do that. It's easy to measure. You can look it up in the book, enthalpy of vaporization. You can also calculate it by taking the enthalpy of formation of bromine gas and the enthalpy of formation of bromine liquid and calculating the difference too. That's another way to do it. Right, with the same techniques we use for enthalpy, using Hess's law. Okay, but anyway, so it's a pretty straightforward calculation. And then we're left with one more, step 3, which is the cooling. Cooling. Right, and the only difference between the heating and the cooling is that we're going to have a negative sign, and the heat capacity is now the gas one instead of the liquid one. So delta S for this transition is going to be the Cp of the gas times len T1 over T2, 298 divided by 330. And this is negative 3.87 joules per Kelvin per mole. Okay, so we've now calculated, we start from here, we've added some entropy, we add a little more, and then we subtract some and we get here, the bromine gas. So that means, therefore, the standard entropy of bromine gas is going to be our starting entropy, which is bromine liquid, plus all 3 entropy changes. Okay, well, we've already measured the liquid one. So this is 152.2 joules per Kelvin per mole plus 8.140. I'm going to stop writing the units here just for simplicity. Plus 88.98 joules, which is, again, the enthalpy of vaporization, how much entropy you gain by vaporizing the liquid. And then you lose a little bit for cooling it. Okay, and then we just add all these together, and we get 245.5 joules per Kelvin per mole. Okay, so that's our prediction. Right, we've made some assumptions here. Well, first we've assumed that we can measure the bromine entropy for liquid, which we can. It's not hard to do. It's well tabulated. And that the heat capacities are constant at at these temperatures. That might not be a good assumption, but we don't know. But what we can do is now we have this prediction we can compare it to experiment. And the experimental value is for S bromine gas is equal to 245.5 joules per Kelvin per mole. We get it right on. Right, this is the power of state functions. Right, that we've tackled a really difficult problem, measuring the thermodynamics of a process that doesn't occur at a given temperature. Right, that's what we want to do, because everything's referenced to 298. And by doing that, we've convoluted this process, or decomposed it into 3 really easy steps: a heating, a cooling, and a boiling step. Right? These are all, a 5th grader could do all 3 of these, right? Maybe they can't measure them, but at least they can set them up. Right? These are really 3 easy steps, and by adding them all together and using the fact that entropy is a state function, or enthalpy, whichever way you want to look at it, we can calculate exactly what the entropy change is, or what the entropy of bromine gas is at a temperature where it doesn't exist in appreciable amounts. Right? And the really powerful thing about that is that now we have this number, and we can calculate the entropy of bromine gas at any temperature by applying the integral rule on changing the entropy as a function of temperature. So this, again, is really powerful. We'll see more and more examples of this next week. Right? I have a really great example with measuring the bond strength of NH3, the NH bond in ammonia. And the way that physical chemists solve that problem, it turns out it's really hard to take ammonia and pluck a hydrogen off and then measure the energy. It's a really tough experiment to do. So they come up with this really clever pathway, this process, to increase the number of steps, but ultimately when you add them together, you get the net reaction that you want. And you get really there's beautiful results, or really precise measurements of the energy for something that you really can't measure otherwise. Right? So this is a really powerful indirect way of measuring things. And in general, thermodynamic measurements are done in that way. Very few of these really fundamental thermodynamic or chemical reactions are measured directly thermodynamically. They're usually measured indirectly because it's much easier to do it indirectly than it is to do it directly. But the great thing is that it doesn't matter. You can do it either way. In fact, when you think about it in terms of uncertainty, you might say, well, we have 3 steps where you might introduce error. Right? So maybe the error, the precision of this path might be worse than doing this. But in general, that's not the case. In general, you can measure heating and cooling and vaporization very, very precisely. And so even the propagated error of doing 3 reactions instead of 1 is smaller than the error that you would get measuring it across the directly, if you will. Okay? And that happens time and time again in physical chemistry. It's easier to do something indirectly because everything's a state function. Any questions about that? Okay. What time is it? Oh yeah, so let me just talk a little bit more about entropy, and then we'll call it. I want to talk about one more thing, and talk about talk about trends in entropy. Just as an example, I just want to kind of get a sense of how entropy changes as molecule complexity changes, because you can actually predict very easily what the change of delta S is just by looking at a reaction or looking at the products of 2 different species. So for instance, let's compare 2 different isomers. One of them is going to be acetone. All right, and what's another? Here's another isomer, oxetane of acetone. You can confirm that these have the same formula. They're structural isomers of each other. And the question is, which has greater S bar? That's a tricky question. But there's a really interesting way to look at this, is that entropy usually scales degrees of intermolecular motion, freedom. So the more ways a molecule can move internally, the higher the entropy. So let's look at these 2 species. Let's start with oxetane. And I'll just draw the H's explicitly, just so you know they're there. How can this molecule move internally? Right? What kind of motions does it have? Well, they both have vibrations. And in fact, you can show they have the same number of vibrations. We won't talk about that, but they have the same number. But there are other types of motion that can occur that aren't really vibrations. For instance, this molecule can pucker. Right? If you think of this, maybe for instance, ooh, that one's dead. If you think of this, maybe this isn't the correct structure of it, but maybe you can think of this as, let me see if I can draw this. A flat plane where you have a hydrogen pointing up and a hydrogen pointing down. Like a square. It doesn't actually look like this, but it looks roughly like this. If you think of it flat, maybe one thing that we can do is like an envelope motion, where this puckers up, or maybe this puckers down. Right? You can kind of move the system like this. You can pucker it up and down like that. And so there might be some internal motion that this system can have with this kind of large ring motion, right? The ring kind of vibrating and oscillating. We call this ring puckering. Right? And so having this kind of puckering motion adds to the entropy. But acetone in particular has a very interesting feature. If I draw this with the carbon and oxygen being in a plane, ooh, let's see if I can do this. is tricky. Again, you have 3 hydrogens. These are really poorly drawn, you'll give me. Sorry. There we go. You have 3 hydrogens, and what you can show is that each of these are equivalent. This one is the same as this one because you can rotate by 120 degrees. HB and HC, for instance. Let's just label them. Right? And if you rotate them by 120 degrees, you get the same structure back. Right? There's this internal symmetry in the molecule. Sorry, this is HC, this is HA, and this one is HB. And then, of course, there's CH3 on this side. Right? So you can rotate this, you can rotate the methyl groups by 120 degrees, or 110 degrees or whatever, and 120, excuse me, and you can recreate the same structure. And you can do that for both of these, right? You can do, these are also all equivalent in the same way. You can rotate this methyl group 120 degrees and get the same structure back. And likewise, if you rotate the molecule along this mirror, if you mirror the molecule along the plane of symmetry, and bring this methyl group over here and this one over there, you'll realize that these 2 methyl groups are also equivalent to each other. So the protons are equivalent and the methyl groups are equivalent. So you have all these internal motions, right? You have this motion of the interchange of the methyls. You have interchange of methyl groups by mirror plane, and interchange of protons or hydrogens, 6 hydrogens, by what we call by internal rotation. Right? You're rotating the methyl group. You end up having a very, very large excess of internal motions, right? And so the entropy for this system is much higher than you would expect, because for every methyl structure, you have 3 equivalent methyls here, 3 equivalent structures here with the methyl protons moving, another 3 over here, and then when you add the mirror plane, I think that comes out to 18 or something like that. There's 18 equivalent structures for acetone, right? So there's 18 equivalent arrangements that acetone can have, right? So W for this, the number of arrangements for the system in equilibrium, is much larger than it is here, because you can't interchange these hydrogens freely, right? In order to make this hydrogen this one, you have to break the bond, and you have to break this bond, break both bonds, rotate it, and then reform the bonds, right? That's never going to happen. But here, you just have free rotation of these hydrogens. Right? They can rotate freely and interchange freely. And so there's all this extra amount of motion in acetone, and because of that, the entropy of acetone is naturally greater than the entropy of oxetane, because acetone in some ways has more degrees of freedom, right? More degrees that can move around and more arrangements of the system that are equivalent. Right? All these equivalent protons and stuff in the planes of symmetry. Right? There's only one plane of symmetry in this molecule effectively, and it's the one that runs along here. Right? There's only one plane of symmetry. But there's many planes of symmetry in acetone. And the more planes of symmetry you have, so more points of symmetry, more planes of symmetry in a molecule, higher its entropy. Right? Because there are more arrangements for that molecule to exist in. So in some ways, entropy is associated, again, it's associated just with an arrangement of a system. And so internally, you have many ways that you can arrange a molecule that are equivalent, 6 protons in a plane symmetry, then the entropy is going to be higher. Right? So molecules that have very little symmetry or are very rigid have very low entropy, and ones that have a lot of symmetry and a lot of internal motions have very high entropy. Another point that I'd like to mention is that entropy tends to scale with the size, the mass of the atom or the molecule. following stout time. So I'm just going to write this here. So in general, and we'll be done, increases with increasing atomic or molecular size. So for instance, the entropy of helium is less than that for neon, for less than that for argon, for less than that for krypton, for instance, for the noble gases. For halogen acids, like HCl, HF, HF is less than HCl, which is less than HBr, which is less than HI. And likewise for X2, for halogen gases, F2 is less than Cl2, which is less than Br2, which is less than I2. So in general, you can guess an ordering for entropy very easily by just looking at mass, looking at symmetry, and looking at internal motions. Okay? And so the more mass you have, the more motions you have, the more freedom in your molecule you have, or the more electrons for that matter. Typically the entropy is higher. Right? It tracks very naturally with mass and complexity. Okay, that's all I have for you today. On Monday, we'll come back to thermodynamics. We'll spend one last day on thermodynamics. I'll give you some cool examples. We'll talk about combustion engines. We'll talk about some chemistry. We'll talk about the sun. And then we'll move on to phases after that. Have a lovely weekend.
Thank you.
Enjoy. I think there's going to be some nice days this weekend, so enjoy it.
I hope for the best.
I'll see you like this weekend.